didn't realize we were having July 5th off. I don't have the time for it. Luckily, you're not going to see 4-1 again in Calc 2 or Calc 3, or I don't know if you're, ever going to see it again in your whole life. I don't think I ever used 4-1. It was just a hard section that you learn and then that's it. So I'm not super worried about it if we don't come back to it. But everything that we're doing in 4-2, 4-3, 4-4, 4-6 is very foundational. And we will do the applications in 4-8. We just might not have time to come back to 4-1. So I'm starting with 4-2 tonight. All right, and if you guys are feeling burned out, I'm starting to feel a little burned out too. It's okay. It happens. We are almost to the point where we just have 3 weeks to go. So we have today, and then you've got your asynchronous weekend homework, and then we have 3 weeks to go, and that 3 weeks is going to fly. So if you're feeling burnt out, you got to steer the course. You got to stay with it, because I understand. I know you feel like you're just constantly like turning around these tests and constantly starting new material. I feel the same way. I feel like I'm constantly just grading tests, writing tests, grading tests, writing tests. And it's like as soon as I get done grading one, I'm making asynchronous lessons, and then I'm writing a new test. And it's, I know, I feel you. It happens like this in the summer, unfortunately. But it's going to be over soon enough. Then you'll have a whole new set of issues in the fall after your break. All right. Any questions before we begin? So chapter 4 is all about applications of the derivative. So we'll start with 4-2, which is about maximum and minimum values and critical numbers. Now, a lot of the concepts in 4-2 are going to look sort of familiar to you, because we've kind of been planting the seeds with this stuff for a while now, as far as the idea of having a maximum or minimum value. And if you feel like, wait a second, we've never talked about this, we actually have, because anytime we talk about when we have a horizontal tangent line, we're talking about a place where your graph starts to level out, whether maybe it levels out as it's heading up and then stops and comes back down again, or maybe it's the opposite. It could be the case that maybe your function's decreasing and all of a sudden you hit this horizontal tangent line and then it begins to increase again. But we're going to talk about this idea of a maximum and minimum and when you know that you would have one. And we're going to relate this back to when you might have a horizontal tangent line on your curve. First, we're going to talk about absolute extrema. So I actually have quite a bit of definition for you here in this first section. So bear with me. I feel like that happens at the beginning of a new chapter. Absolute extrema. Teeth. We're going to let f be a function defined on some interval I. If there's a number u in the interval for which f of u is greater than or equal to f of x, for all x in the interval, then f has an absolute maximum at u. And the number f of u is called the absolute maximum value of f on I. Now I'm going to draw you a picture of this so you can get an idea of what this means. I know sometimes when you see it all in words, it's kind of hard to visualize, but I think this is actually a concept that's going to be pretty intuitive for you. So I'm going to kind of draw it out. And of course, this concept can be represented by an infinite number of graphs. I'm just sort of going to give you an idea of something that could be representing this situation. And notice, by the way, that I'm just giving you some interval from A to B in this case. So we're going to have some left and right endpoints to the interval that we're looking at. Now, our value of u is going to be somewhere inside this interval. There's a number u in the interval for which the function value of u is greater than or equal to the function value at any other x. So u has to be the highest point inside of here. So I'm just going to eyeball it. But this would be an example of a situation that meets this criteria. So you have this function f. It's in our case, we're just looking at this curve. We're looking at this closed interval from A to B, and there's this number u for which the function value at u, so the y value, is greater than any of the other y values in this interval. So if you were to look at the function value over here, that would be f of u, and this would be the highest value of y that you would see. Like, for instance, f of a would be over here, and f of b would be this value. So when we talk about a maximum value, we're talking about the actual y value that is obtained at this x value u. Now, in this case, we were just looking at a specific interval. So you might be wondering, like, okay, well, what if I, follow this curve to the left, and clearly this arrow indicates that the behavior of the graph is heading upward again. I mean, is it possible that it's going to keep going up, and then, we might have a value that has a function value that's greater than f of u? It's possible, but it doesn't matter, because in our case, we're just looking at what happens on a closed interval from A to B, which is really what we're going to be focusing on today, is just this idea of absolute extrema. Tomorrow, I say tomorrow, but your asynchronous weekend work will be a little bit more generalized for finding different places on your curve where you might have maxima or minimum values. But for right now, we're focusing on what's happening inside this interval, and we don't care what happens to the left of A or to the right of B. So this is just your interval I that we're looking at here. Now, you could have a similar situation and be looking at minimum values. And again, this, I think, is a pretty intuitive concept, but let's say that you had, again, a closed interval from A to B, and maybe you had a situation that looked a little bit more like this. We can talk about the minimum value on the function by saying basically the same thing in reverse. If we can find a value, f of u, such that f of u is less than or equal to f of x for all other x in the interval, then we could say that we have an absolute minimum at u, and that f of u is the absolute minimum value of f on the interval I. Oh, you know what? Let's call it v, not u, because we got to switch this up. Call it v. So in this case, you might have something like this, where you would have a minimum value that is the value f of v, so that y value. Should we call our function f still? Sure, I'll call it f. So I'll give you this definition a little bit faster this time because you can kind of see now how it's basically the same idea, except we're just going to be looking at values where f of v is less than or equal to the function values for all other values of x. So if there's a number v in the interval I such that f of v is less than or equal to f of x for all other x in I, for all x in the interval. So for any other value x in the interval, f of v is less than or equal to all the other function values, then f has an absolute minimum at v. And the number f of v is the absolute minimum value of f on I. Okay, so those are your formal definitions for absolute maximum and absolute minimum values. Now, I had mentioned earlier, eventually we're going to generalize this and you're going to find more than one place where you might be able to localize that value, which I'm going to define for you in a couple minutes here. If you are looking at this definition and saying like, well, it says absolute extrema. Well, extrema is just the plural. So we'll go ahead and say that the values f of u and f of v are sometimes called absolute extrema. Or the extreme values of f on I. Okay, so that's a little definition for you. A little bit more definition for you before we really get into the heart of being able to find these extreme values. Before I continue, does anybody have a question here? Okay. Wonderful. So let's talk now about kind of localizing these values. So our next definition is for local extrema. All right, let f be a function defined on I. Let u and v be numbers in I. And if you feel like you're just writing stuff down and it doesn't mean anything, think about what it is that you're writing. We're talking about a function that's defined on I. That means that everywhere on this interval, your function is defined, which means that you're not looking at places where you have any, big asymptotes and breaks in the graph. I don't know what else could cause you to not be defined. A square root being negative, you're not dealing with anything like that. Your graph is defined on this interval I. U and V are numbers somewhere inside that interval. If there's an open interval in I containing U, so we're going to open up the interval now. So if there is an open interval in I containing U, so that f of u is greater than or equal to f of x, for all x and I, well, I'll say for all x in the open interval, because we're talking about an open interval inside I, then f has a local max or relative max you're going to see it referred to as both local and relative, and you can kind of use those terms interchangeably. At u, and f of u is called a local maximum value. Okay, you finish writing that. Hold on. Okay, so this time we're talking about having this interval I, but now we're looking at an open interval inside here for which f of u is greater than or equal to f of x. So again, let's see, I'm also going to say, instead of repeating this definition again for a local minimum, I'm just going to say similar definition for local minimum, because we don't want to have to write that again, just to switch out this piece. Similarly, if f of v is less than or equal to f of x, then f has a local min or relative min at v. And f of v is a local minimum value So I'm also going to give you a picture of this because I feel like it really helps to see this, because maybe it's hard to tell the difference between this definition and what we talked about for absolute extrema. So what we're really talking about here is a situation where maybe you have a lot of highs and lows going on in your graph. Let's try to make it I don't know, maybe something like, yours doesn't have to be exactly like mine, but it would help if it's close. Okay, so let me sort of show you the difference between an absolute maximum and an absolute minimum and a local maximum and a local minimum. So the highest Y value obtained on your curve from what you can see is going to be referred to as the absolute maximum. So in our case, from what I can see on my graph, this is going to be the highest Y value that I see no matter what. Now, I know that I have a peak here and I have a peak over here. However, the absolute highest value it looks like I'm attaining is right here. So I'm going to call this one the absolute max. Now, if you're looking for the absolute lowest value, in this example, it's kind of hard to see, but it's going to be this one right here, the absolute smallest. And let's chop this off, actually, because I don't want this to be confusing with this end over here. Maybe it's something like this and something like that, maybe. I'm going to cut off my interval. So we're still talking about this interval I. I have an absolute maximum, and then I have an absolute minimum right here. And if you don't want to keep writing absolute, that's fine. ABS is totally fine. So this would be an absolute minimum value. This follows that first definition that we looked at for absolute extrema. This, for all other values of x inside this interval, this would be the value u that would have f of u, the highest function value. And then this one would be that value v that has the lowest function value in this interval. However, once we start talking about local extrema and we're looking at this second definition, now we're talking about opening up an interval inside I that contains some value. I know I already labeled this u, but we're going to look at maybe a different value that might be the lowest value in that particular open interval. So let's say that maybe I just wanted to focus on what was happening from C to D. So let's say I just use an open interval inside of this interval I, and I was just focusing on what happened inside of here. If I did that, well then inside this interval from C to D, and again, if you want to sort of pull that up here, make sure that we understand the difference. Here's our interval I. What I'm looking at now is this local neighborhood. So I'm inside this big interval, but I'm looking at a little neighborhood. So imagine if you're, talking about I being Elgin, and then maybe this little interval from C to D is a little neighborhood inside of Elgin. So, there are different parts of Elgin that are different. And maybe you're looking right now at this neighborhood from C to D, and we're just focusing on that. So, we can't just judge Elgin on the whole just by looking at I, but we can look at each little neighborhood and kind of see the differences. And that's what we're really doing here when we're talking about these function values. So this is Elgin, and then the interval from C to D is a neighborhood within Elgin. And in that neighborhood, I'm looking at the highs and the lows. So the local maximum would be this value here at the top of the hill. Now, the local minimum would be the smallest value that actually occurs inside that interval. And again, it's kind of hard to tell in the way that you drew this. Yours might look slightly different than mine, but it looks like for me, that value is going to be right here, because at C, I'm a little bit higher on this curve on that end point. and at D, I'm a little bit lower. So I would say that if I was just focusing on this open interval from C to D, then this point right here would be my local minimum because it's the absolute lowest value that I would actually obtain inside that interval. So we can kind of split this up in ways like that. So again, you know, if I were to look at all of these little peaks and valleys, I could find places where we would have local extrema and absolute extrema. So another place, you know, clearly within I where I'd have some local extrema if I was just looking at these highs and lows would be maybe right here. I can definitely find a neighborhood within I such that this value right here is a local minimum. I can find a neighborhood such that that is true. So I would label it that way. And then again, looking over here, I have this value between A and C, or I could also say that this is a local minimum because I can definitely find some neighborhood within I such that this value right here is a local minimum. Now, normally we don't talk about endpoints within an interval. So you might be wondering, well then, okay, at B, would I say that this is a local maximum because this is the endpoint of the interval? In this particular case, because this is an endpoint within I, we can't actually come up with a neighborhood around that point. I would have to be able to say like, okay, I'm looking for a neighborhood from here to here, where that's my absolute lowest or highest value, which I can't do. So we're not going to discuss the endpoints as far as local extrema is concerned. Okay, so that's kind of my pictorial representation of local versus absolute. So the absolute is like the absolute highest or absolute lowest value that you're obtaining on an interval I. And then when you're talking about local or relative max and min, we're talking about can we find a neighborhood such that this would be the maximum or minimum value. And that's where you're going to just be looking at these sub peaks and valleys. Peaks and valleys, yes. Okay. Any questions there? Okay. All right, so kind of piggybacking off that idea, I have for you the extreme value theorem. If a function f is continuous on the closed interval from A to B, I'm going to be abbreviating continuous as CONT dot all the time because we're going to be talking about whether or not our function's continuous and differentiable throughout this whole chapter, and I don't want to keep writing it every time. So if f is continuous on the closed interval from A to B, then f has an absolute max and an absolute min on the interval. So it must be the case, as long as f is continuous, remember f is continuous if you can draw the function without ever having to lift your pencil. If that's the case, then we can guarantee that f is going to have an absolute max and an absolute min on the interval. So it's going to have one of each. Can't have more than one. Unless it's the same value. I guess I should specify, but we're going to see some examples of that. That leads us to another small little theorem. So at least I'm past the big stuff now. I'm just going to give you a couple little things before we get going on this. From that, a condition for local max or local min. So moving back to local. If F has a local max or local min at C, then either, and this is very important. Okay, so if F has a local min or local max at C, then either it must be the case that F prime of C is equal to 0, meaning the derivative at that value equals 0, which makes sense because that we know if we set the derivative equal to 0, we're probably going to get some maximum or minimum value. If we do have a max or min, we know that either this is true or that F prime of C does not exist. Okay, so what that could look like might be something that we saw before in our previous couple of chapters. It could be the case that maybe you have a function that does something like this. And at this point right here at C, we have that F prime of C equals 0. Because remember, if F prime of C equals 0, that means the slope of the tangent line at that point is 0. And if the slope is 0, that means the tangent line itself is horizontal. So you had all these homework questions that asked you to find places where your function would have a horizontal tangent line. And what you did was you took your function, found its derivative, and set the derivative equal to 0, and then you solved for values of x where that was true. We're basically doing this right now, talking about that process in reverse. We're saying that if we have a local max or min, then it must be the case that either this situation is occurring where F prime of C equals 0, or you might have, I mean, there are any number of things that could happen here in the case of a DNE. But remember we talked about a case where F prime of C might not exist. So we said that a function might not be differentiable if you're looking at a sharp point. So it could be that at this value C, maybe you have like a sharp point in the graph. Could be doing something like that. So in this case, we would have that F prime of C does not exist. And remember, that would occur because you had a sharp point. So that could represent a maximum or minimum value in that case if you take the derivative and it doesn't exist. It's a possibility. So you can kind of see where this is going now. We're going to be talking about how to find local max and min, and then absolute extrema. And to do that, we're going to be looking at places where F prime of C equals 0, or F prime of C does not exist. All right, I have one more small theorem and one more small definition for you, and then we're going to hit the road running. I don't mean we're going to leave. I mean, we're going to like get into a bunch of examples where you can see this occurring. Renee, did you grade our test yet? Renee, I am 40% done grading your tests. That means that there are 25 of them and I have graded 10 of them. And you were the first one to submit, so yours is graded, but I'm not posting everything until everything's graded. But if you email me, I'll probably go ahead and let you know what your grade is. If you submitted early, I grade them in the order in which they were received. So. Oh, you know why D2L is showing you as 0%? Because I have it set so that all ungraded items are treated as zeros. So like if I don't enter a score for something, it's automatically a 0. But that's just because the grade item, it's like in a holding cell basically. So it's just waiting there for me to grade them. Don't worry, I have your test. Everything's good. If I remember correctly, it was good. Since we're on the topic of tests, they've been great so far. The 10 that I've graded, I don't think anyone has gotten less than a C. Maybe someone has gotten a D, but they've been really good overall. Can't remember, but nothing has been just jarringly bad. Like someone might have gotten a 68. I don't know, but they've been really good so far. Which is, I don't want to say surprising, but usually test 2 goes much better than test 3. And so far, from what I've seen, test 3 has been better. So that's good. Yeah, so don't worry if you see a 0 in the grade book. It's just waiting for me to submit everyone's grades. When I get done, I say publish all feedback, and then it spins around and spins around. And then eventually everyone's grades kind of filter in. Okay. Okay, good. I felt like I needed that break. I'm actually glad she asked us about that because I needed a mental break from all this theorem definition business. Okay. All right, theorem. And I'm getting into the really good stuff now too. If you thought it was good before, you haven't seen anything yet. If a difference function f has a local max or local min at C, difference function. If a differentiable function. If a differentiable function f has a local max or local min at C, then f prime of C equals 0. Interesting. So if we have a local max or local min at C, then it must be the case that f prime of C is equal to 0. Okay. Then the last thing that you're going to need to know is the definition of a critical number. And we're going to be looking at critical numbers all the time throughout chapter 4. And then when we move into chapter 5, we're going to shift gears. Definition. Critical number. Now, if you have not been writing anything down up to this point because you're one of those people who hates to write and you're just like, la-di-da, I'm going to wait till she's done, write this down. I know how you guys are. Some of you are just like furiously writing everything I write, which of course, like you hold a special place in my heart. But those of you who have not written anything, now's your time to shine. Critical number. A critical number of a function f is a number C in the domain of f for which either f prime of C equals 0 or f prime of C does not exist. And, you know, even I'm going to put a little squiggly in the domain of f because I want you to make sure that you remember that that must be the case. Your critical number has to be some number that's actually in the domain of the function. All right, so we're going to be doing a couple things here today. The first thing I'm going to show you is finding critical numbers. And then we're really going to be doing that for the rest of 4.2. but we're going to sort of do that in conjunction with locating extreme values. So I'm going to give you a couple of examples here to get your feet wet with finding critical numbers first, and then we'll talk about finding extreme values on closed intervals. Okay. Wonderful. Example 1, find all critical numbers of the function. The first one we're going to look at is f of x equals x squared minus 7x plus 3/2. And you're going to look back at your definition for a critical number. A critical number f is, a critical number of a function f is some number c in the domain of your function for which f prime of c equals 0 or f prime of c does not exist. Now notice that this is a polynomial function. The domain is all real numbers. So you're not going to have to worry about any values that are excluded from the domain. But go ahead and take the derivative. This is always what you're going to do. Take the derivative, set it equal to 0, and this is going to give you critical numbers where you might possibly have a maximum or minimum value on your function. When you take the derivative, you get 2x minus 7. And then you're going to take your derivative and set it equal to 0. In the future, I'll probably just set it equal to 0. But, oh well. All right, so take f prime, set it equal to 0. You get 2x equals 7, or x equals 7/2. This is your critical number. It's in the domain of the function because the domain of the function is all real numbers, and it's a place where the derivative is equal to 0. So if you were to actually graph this function, first of all, it's a parabola. You know it opens up because the lead coefficient is positive, but you would find that somewhere sitting on this parabola at 3.5, somewhere in here, you would have an absolute minimum value because we know the parabola opens up, and it must be the case that the lowest value on this parabola is here. So I don't know, maybe something like that. We don't know, but we know whatever is happening, it's happening right here at 7/2. So this is where we would have that horizontal tangent line. And we'll do one or more of these using a trig function. I learned something when I graded those first 10 tests. It was that we don't know how to use a unit circle, and we don't know our trig function values, and it saddened me. But I guess it didn't really surprise me. H of x equals the cotangent of x plus 2x. Now I have to give you some sort of interval here because I'm not going to ask you to find every single critical number in the world. Otherwise, we'd have to generalize this. And I just want you to find the ones in this interval from negative 2 pi to 2 pi. So we're going to take the derivative, and then we're going to set it equal to 0 and solve for these values of x. So the derivative of cotangent, it's cofunction, so it's going to be negative. The derivative of tangent is secant squared. So for cotangent, it's negative cosecant squared of x, and then plus 2. Equals 0. go ahead and add the cosecant squared to both sides, and you get cosecant squared of x equals 2. And if you're trying to solve this equation, if you'd like, you can just talk about the actual cosecant value itself without having to square it. Take the square root on both sides. Remember, if you're going to take the square root of both sides, you need to include that plus or minus sign. So it would look like this. And if you're still just like, okay, yeah, I have no idea where the cosecant of x would be plus or minus the square root of 2, that's fine. Use the reciprocal. 1 over the cosecant of x is the sine of x. Actually, so I should say 1 over sine x. So I'll say cosecant x equals 1 over the sine of x. So we're going to rewrite this here. So if this is the case that the cosecant of x is equal to 1 over sine of x, well, then I can take the reciprocal on both sides, or if you want to think about it as cross multiplying, you can think about it that way. Multiply both sides by sine x, divide both sides by plus or minus the square root of 2, whatever it is that you need to do. We can say that the sine of x is going to be plus or minus 1 over the square root of 2. And maybe you took trig at ECC, or in high school, they made you always rationalize, and you're just like, yeah, this still means nothing to me. Well, 1 over the square root of 2 is the square root of 2 over 2. Those expressions are equivalent. So hopefully now this is ringing some bells where you're like, oh yeah, I remember this, square root 2 over 2. And then you just have to remember what value of x gives you a sine value of the square root of 2 over 2. And we know that the reference angle is going to be pi over 4. I'll just say ref theta. 45 degrees, pi over 4 radians. The sine of pi over 4 is the square root of 2 over 2. But remember, I have 2 places in the unit circle where that's going to be positive, and then I have 2 places where it's going to be negative. So we're going to have to find all of those places, and then we're going to have to look also at the interval from negative 2 pi to 0, because I asked you for this whole thing. So first, let's focus on 0 to 2 pi. So let's say in 0 to 2 pi, we have x being, well, pi over 4, that's in quadrant 1. We're also going to have sine being positive in quadrant 2. And the reference angle is pi over 4. So pi minus pi over 4 is 3 pi over 4. And then the negative variation of this for sine is going to occur in quadrant 3 and 4. Sine is negative in 3 and 4. So pi plus pi over 4 is 5 pi over 4. 2 pi minus pi over 4 is 7 pi over 4. So these are all of the places where you're going to get sine of x is plus or minus the square root of 2 over 2 in 0 to 2 pi. Then you'll want to focus on what happens from negative 2 pi to 0. Go ahead, Busan.
Can you explain how you got pi over 4, 3 pi over 4?
So the sine of pi over 4 is root 2 over 2. That you can look at your unit circle for. You should have done that extensively in trig, where you had to just know those values. You can always double check it in your calculator by entering sine pi over 4, not e, pi over 4. And then just double check that that's equal to the square root of 2 over 2. And you'll get the same value. So you know that pi over 4 is that reference angle, and then you're kind of just going through and looking at all of the places where that's going to be true. And sine is positive in quadrants 1 and 2. You're going to have the same value at 3 pi over 4. So you can check that too. You can go back and say, okay, well, sine 3 pi over 4, same value. Now, as soon as you move into 5 pi over 4, you end up with a negative value, but that's fine. You want it to be also negative. And then again, you can go up to 7 pi over 4. But all of these places are places on your graph where you have a reference angle of pi over 4. So pi over 4, pi over 4, pi over 4, and pi over 4. So that's something that you learned how to do back in trig. So these are the 2 positive ones, and those are the 2 negative ones. Other questions about these angles? Okay. So we're going to do the same thing from negative pi over 2 to 0. So all the way, I mean, we're basically just going to repeat these again, just in their negative values, because I can obtain the same value by taking 0 and subtracting pi over 4. So negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, and negative 7 pi over 4 gets us almost all the way to negative 2 pi. And these would be your 8 critical numbers in this interval. If you are really stuck on this, then one thing I was suggesting to students is try the free tutoring online if you're stuck on some of this trig stuff, because I can't really spend a whole bunch of time in class on it, because it is something that you should have discussed extensively in trig. But try the online tutoring. I don't know, I haven't heard much feedback on it this semester, but I know last semester I had a student who was in there just like every day, and she found it really helpful, and she got to know the tutors, and I mean, she was in there a lot, just kind of even picking up some of that prerequisite knowledge. I always find that in calculus, that's where my students go astray, is just not having a really strong background. I had a friend who wanted to go back to school for computer science, and he took a placement test, and it placed him in algebra, and intermediate algebra. So it'd be like the ECC equivalent of like 098 or something. No, they placed him in college algebra. That's right. And he texted me and was like, "Ugh, I don't want to take college algebra. I just want to go straight into calc. I want to try to clip out of it. I just want to like try to take the test and get out of it." And oh, I yelled at him, and I was just like, "Do not. You're not going to be prepared for calc because you don't. It's been a while since you've seen this material." And sure enough, so he's like, "Okay, fine." And he took the college algebra class, and he struggled like the whole time in it. And I didn't want to say I told you so, but just like, listen, you gotta have the strong background knowledge in order to do these problems, because at this point we are okay with finding the derivative. I mean, that's the calculus part. It's just now applying your trig knowledge. So make sure that that if you need to brush up on your trig, go to the tutoring center. That's what it's there for. I mean, it's tax dollars at work. It's free. They want to help you. So if you need information about that, it's in your syllabus, but you can also send me an email too. Because like I said, on the tests I graded, there were a lot of people who are getting their trig values incorrect, which was causing some of their, what was it on? Oh yeah, it was like finding the equation of a tangent line. And everybody had the derivative right, but then when it came down to like finding the sine of pi over 6 and the cosine of pi over 6, like the values were all wrong. And it wasn't just one person, it was several people, and I've only graded 10 so far. So so make sure that you're brushing up on that trig, you guys. Don't mean to harp on any one person, just it's a general thing that I encounter every time I teach calc. All right, so now we have the critical numbers. That's what I asked you to find here. We're going to use these to find absolute extreme values. So I'm going to give you the definition here and some instructions on how to do this. But basically, I'm going to be giving you a function. And what you're going to be doing is identifying possible values inside the interval where you're going to have local extrema. You're going to find the local extrema by finding places where the derivative is equal to 0 or does not exist. And then what you're going to do is you're going to compare those local extreme values to the values at your endpoints. Because when we're talking about absolute extreme values, we are going to talk about the actual values at the endpoints themselves. And we're going to compare those and see which value is the biggest and which value is the smallest. So that's the theorem that I'm going to give you next, locating absolute extreme values. Okay, so we're going to let f be continuous on the closed interval from a to b. Then the absolute max and absolute min of f are the largest and smallest values. Respectively, found among the following. I don't know why, but I just got really excited about this. I don't know what it is about finding absolute extreme, guys. I'm really excited. The values of f at the critical numbers inside the open interval. So we're going to look at the function values, not the value at the derivative. We don't care about that, but we're going to look at the actual function value. So the y value on your function at your critical numbers. So how high does it go? How low does it go inside the interval? And then we're going to look at f of a and f of b, which are the values of f at the endpoints. Remember, we're talking about this on a closed interval from a to b. So we're going to evaluate the function value at your left endpoint a, the function value at your right endpoint b. We're going to compare those to the function values at your critical numbers, and we're going to figure out what is the absolute highest y value and the absolute lowest y value that you're going to see on your function. And I'm going to summarize that in these steps so that you are very clear on what it is that you're supposed to be doing. So these are steps for finding absolute extrema in the closed interval. Put a little star by it. You can highlight it if you want. By the way, before you take your test on chapter 4, which is actually shockingly not next week, you actually have a week off from taking a test. Watch, I'm going to look at my schedule and I'm going to be wrong about that. But I'm pretty sure I already looked and there's no test next week. I mean, how could there be? You have a test next scheduled for July 19th, which is Monday, a week from Monday. So this upcoming Monday is the 12th. The Monday after that is the 19th. So you'll have the weekend to go through this chapter 4 work. Oh, and notice on your schedule that we don't go over 4.5. That's a Calc 2 topic at ACC. We don't do it in Calc 1. But we will spend quite a substantial amount of time next week in 4.6. So probably like 2 days of lecture we'll spend on that, but we'll see. So what I'm probably going to do now that I'm looking at next week Your asynchronous work is going to cover all of 4-3. Oh, you know what? I'm looking at the wrong schedule, but your test date should be the same. I updated your syllabus. I just didn't print out the update. Your asynchronous work is going to cover 4-3 and maybe a little bit of 4-4. And then next week we'll do 4-4, 4-8, and 4-6. I might even start out with, before I do 4-6, I might do 4. No, 4-8 I'm going to move. I think I did already. I shouldn't be looking at this schedule because I didn't print out the update and I don't have it on this computer. But your applications are in 4-7. Either way, your test is not next week. That's all I was trying to say. But before your chapter 4 test, what I was going to tell you is I'm going to remind you of this because you're going to forget about this because you're going to go through so much other stuff in this chapter, even though it's not that many sections. And then you're going to totally forget this, finding absolute extrema in a closed interval. So I'm going to remind you, don't forget about finding absolute extrema in a closed interval. And as long as you remember to just look at your notes clearly, you should be good to go. At least it's open notes, so it shouldn't be like, oh my gosh, what am I doing again? First, you're going to locate all critical numbers in the open interval. Numbers. And the open interval from A to B. So not looking at the endpoints, we're just looking at what's inside this function. So if you end up getting a critical number at an endpoint, then it's technically not a critical number. The critical number has to be inside the interval. But you're going to look at the endpoints anyway. That's step 2. Or actually, yes, that's step 2. Evaluate f at each critical number and at the endpoints A and B. Evaluate f. I'm underlining that because students sometimes accidentally evaluate f prime. Don't evaluate f prime, evaluate f at each critical number and at the endpoints A and B. So we're going to look at the function values. So the y values on your graph at each critical number and at A and B. Then the largest value is the absolute max and the smallest value is the absolute min. And that's it. All right, I'm just looking at your updated syllabus here. Yeah, so test 4 is still scheduled for July 19th. I usually kind of chop up chapter 5. I don't cover like the entire thing. Like 5.1, I pretty much always skip. I put it on here because I'm really optimistic every semester that maybe I'll have extra time, but clearly that's not happening this semester. Next week, I'm mostly focused on 4.4, 4.6, 4.7. That's it. I might even update this schedule again, but I kind of try to see where I am and then kind of go from there. 4.8, I always put in with chapter 5. It's just that it seemed like I didn't want to have your test on a Thursday, so I popped 4.8 in there. But 4.8 goes along with the chapter 5 material. It's kind of annoying to me that they put it in chapter 4. Okay. But either way, your test is the 19th, which is a week from Monday, test 4. And chapter 5 will go by very quickly. It's very short. Okay, so you have your instructions. Now we're going to do example 2, find the absolute extrema on the interval. I'm going to try to give you a variety of functions here because when you are working through your homework, you're going to see all types of different functions. You're going to see polynomial functions. You're going to see rational functions, radical functions, logarithmic functions, exponential functions, inverse trig functions, all the functions for which you learned how to take a derivative in the preceding chapter. You're going to be seeing in this section with applications, or in this chapter, I should say, with applications. So I want to make sure that I give you a bunch of different types of examples so you're consistently seeing work done with these derivatives. And you might see that the process looks slightly different depending on what type of function you're looking at. By the way, with these, I have to give you a closed interval. Otherwise, you don't have endpoints A and B. So for this one, f of x equals 3x to the 4th minus 8x cubed plus 6x squared minus 24x minus 9. And the closed intervals from 0 to 3. Okay, so we're going to locate all critical numbers in the open interval from A to B. So that means I'm going to take the derivative and I'm going to set it equal to 0. And I'm going to find all critical numbers in the open interval from 0 to 3. Occasionally, you're going to find critical numbers that don't lie in this interval. We're just going to get rid of them because we don't care about them in this case. All we care about is what's happening from 0 to 3. Then we're going to evaluate f at each critical number and at the endpoints and determine which one is our absolute min and which one is our absolute max. So first, to find the critical numbers, we're going to take the derivative. So it's polynomial 12x cubed minus 24x squared plus 12x minus 24. And we'll set it equal to 0. And then I'll remind you of how to factor by grouping and solve if it's been a while since you've done this. Notice that you're seeing a pattern here with the coefficients. That won't always be the case with factor by grouping, but a lot of times it sort of signals to you that this will work nicely. I'm going to try to look really closely at these polynomials because I feel like there might be an example in your book where you can't factor this by grouping and you have to use other methods. And you technically learned other methods in college algebra, but students never remember them. So I'm going to try to look at those a little more carefully before I make the assignment. But sometimes it's hard to see when I eyeball it. If you see something where it turns into some third-degree polynomial where you can't factor and solve, let me know. And then we'll figure out what to do with it. When you're factor by grouping, remember you're looking at 2 terms and 2 terms. You can just kind of group them from left to right the way that you see them. Take out the GCF in the first group. In this case, it's 12x squared, and that leaves you with x minus 2. In the second group, take out a 12. It's a positive 12, so put a plus sign in front of it. And that leaves you with x minus 2. Now remember with factor by grouping, you'll know that you did this correctly if each one of your terms has a common factor, which in this case it does. Your common factor is x minus 2. Factor it out. And what that leaves you with is 12x squared plus 12. And then go ahead and take out your 12 because that is, I guess we could have done that from the beginning. If you thought from the beginning to take it out, then excellent work. When you take out the 12, you're just going to get x squared plus 1 as one of your factors, and then the other factor is still going to be x minus 2. Now, when you use your zero factor property here, you're going to take each factor and set it equal to 0. Well, clearly 12 can't be equal to 0. X squared plus 1 actually cannot be equal to 0 because you would need x squared to be negative 1, which it can't be because you can't square a number and get negative 1. So that one's not going to do anything for us. And then you have x minus 2 equals 0, and you'll solve that and get x equals 2. So you only have one critical number. Double check to make sure that it's actually in your interval. X equals 2 is indeed in the interval from 0 to 3. So it is a critical number inside our open interval from A to B. So I'm going to say it's in the interval from 0 to 3, check. If you ever get a critical number that happens to also be an endpoint, then you're not going to call it a critical number. If it's the only one you have, you might just say there are no critical numbers, and then you would just evaluate the endpoints. Every once in a while, you're going to get a situation where you have no critical numbers. That's okay. You still will need to evaluate the function at the endpoints to determine the absolute minimum and maximum values. But if you see something like that and it's confusing to you, feel free to hit that Ask My Instructor button, and I will answer you back on it just to allay your fears and concerns. Okay. So the step 2 is evaluate your function at each critical number and at the endpoints A and B. So we're going to I always start with f of a. Now a is going to be the left endpoint, which in our case is 0. So I always start with f of 0, and then I move inside the open interval from 0 to 3. So the next place I'm going to evaluate is at 2. And then we'll move to your right endpoint. So we only have the one critical number, so we only have one value inside the interval, and we'll look at f of 3. Now remember, we're looking at f of these values, not f prime. If you want to actually plug in each value, be my guest. You might find it easier to just use your calculator and use the table like we did when we were using all these values for limits. So I'm going to do this using my calculator just because it's faster. You might find that depending on your function, it might be faster to do it by hand. In this case, I don't think it's faster to do it by hand. You can do either one, but sometimes it is faster to go by hand. So if you're kind of like, why am I spending all this time entering this in my calculator? I could have been done with this by now. That's fine. I mean, and look, what if you enter something wrong? Then you should have just done it by hand. So f is 3x to the 4th minus 8x cubed plus 6x squared minus 24x minus 9. And I'm just going to look at the function values at 0, 2, and 3. So I'm going to go to my table. Now mine is still set to ask. If yours is set to auto, remember you're going to have to go in and change your table settings. So second window, and make sure that the independent variable is set to ask. Okay, now go back to your table. I'm going to look at 0, 2, and 3. And I'm going to get 3 different function values there. F of 0 is -9. F of 2 is -49. And f of 3 is 0. What you're going to do now, step 3, is you're going to pick the smallest and the largest value. And hopefully that will be very clear just by looking at them. Sometimes you're going to get funny you might be looking, if you do it by hand, at like exponentials that you're going to have to approximate. I'll probably show you an example like that. But look at the smallest value. Now, make sure that you're considering not absolute values, but the actual smallest value. So even though 49 seems like a big number, it's a negative 49. So this negative 49 is actually your smallest value. And even though 0 seems like such a small number, it's not negative. So in this case, your largest value is actually 0. So when you answer this, you would say that your absolute minimum value is negative 49, and it occurs at x equals 2. So your absolute min is negative 49, and it occurs at x equals 2. And we'll say something similar for your absolute maximum value. So your absolute maximum value is 0, and it occurs at x equals 3. So if WebAssign prompts you for the absolute minimum value, that's the y value. If they ask you where it occurs, that's the x value. So you might want to say the absolute minimum value, just to be very clear, in that when you're referencing your homework, when you're referencing your notes as you do your homework, you understand which one's which. So this is the y value, and then it occurs at the x value. Okay, questions on that one? All right, so these are not too bad. I don't think we've gotten used to taking derivatives. You've gotten used to setting them equal to 0 to find critical numbers. You just didn't know what they were when you were doing it. But now you do, and we will work through some more examples. Let's do a rational function. X squared plus 5 divided by x plus 2. And we're going to look at this on the interval from -3/2 to 3/2, which, remember, is about it's exactly -1.5 to 1.5. So this one's going to use the quotient rule when you find the derivative. That's going to be the fastest way to get you there. I know sometimes we try to avoid the quotient rule like the plague, but there's really no way around it in this point, in this instance. All right, so let's use the quotient rule. F prime g minus f g prime. You guys, the first 10 of you at least, did an awesome job showing your work when you were using the product rule. I saw so much of like f prime, g prime. I didn't have to wonder where anything came from. Everything was labeled beautifully. As a general rule, I was so happy with that on your tests. And the use of the product and quotient rule was really good. I can tell you've been practicing. All right, so f prime g minus f g prime all divided by g squared. So I feel like I'm not going to keep labeling it. I'm going to keep saying it, but I'm not going to keep labeling it because I think you're getting pretty good at that at this point. I don't need to keep doing that. Okay, one thing I want to note right away is that x equals -2. I should have noted this before. Note. X equals -2 is not in the domain of f. So because of that, it cannot be a critical value. Or we'll say it cannot be a critical number. In case it comes up, because remember, you're looking at places where the derivative is either equal to 0 or where the derivative does not exist. And you're going to find that the derivative does not exist when x equals -2. However, it's not in the domain of f, so it doesn't matter to us anyway. But let's go ahead and simplify our derivative. Sometimes it's helpful just to look at the domain right away. 2x squared plus 4x minus x squared minus 5 divided by x plus 2 quantity squared. So distributing in the numerator, and remember to distribute that negative sign in your second set of terms. 2x squared minus x squared is x squared, and then plus 4x minus 5 divided by x plus 2 quantity squared. Okay, so we're looking for f prime of c not being equal to 0. So we're going to take f prime of x and set it equal to 0 and figure out where those values of c might be. Remember that when you're taking a fraction and setting it equal to 0, in order for the fraction to be equal to 0, you need the numerator to be equal to 0. So for f prime of x to be equal to 0, what we need is x squared plus 4x minus 5 to equal 0. Don't worry about the denominator. If the denominator is 0, then f prime of x does not exist. If the numerator is 0, then it's 0. So set this equal to 0, and then we're going to factor and solve to find these values of x. The two numbers that multiply to give you -5 and add to give you +4 are +5 and -1. So factor that, and then use the zero factor property to come up with two critical numbers, x equals 1 and x equals -5. Now, once you find those critical numbers, don't put a box around them right away. You want to make sure that they're actually in your closed interval. If they're not, then we don't care about them. We're only focusing on what's happening from -1.5 to +1.5. Any other value doesn't make a difference to us because we're only looking at what's happening in this closed interval. Notice that x equals 1 is in this interval because 1 is between -1.5 and +1.5. That one you can put a box around. However, x equals -5. Well, -5 is less than -1.5. So even though it's a critical number, we're not going to use it. We're going to say that it's not in the interval from -3/2 to 3/2. So you found it. I want to see it when you do this on your test. I want you to actually find both of the values for me. But then if one of them is not included, just X it out. Don't use it. Don't just not write it, though. Write it, check it, X it out. Okay. So I had mentioned that we were looking for places, and I'm going to go back to this definition here. Values of f at the critical numbers, yada, yada. Maybe I need to go back a little bit further in time. So much paper, you guys, so much. Okay. Extreme values. Condition for local max and min. If f has a local max or min at c, then either f prime of c equals 0 or f prime of c does not exist. That's not what I was looking for. Oh, there it is. I should have highlighted it like I asked you to. The critical number of a function f is a number c in the domain of f for which f prime of c equals 0 or f prime of c does not exist. So what I normally have you do is if you have a rational function, you're doing two pieces here. One of them is f prime of x equals 0, and then you're taking the numerator and setting it equal to 0. The other one is f prime of x does not exist. Now this happens when the denominator equals 0. We can't divide by 0. That would make the function not exist. But we already stated that in this case, x would have to be equal to -2, which is not in the domain of f. So x equals -2 is not a critical number, and we're not going to even look at it. It doesn't matter anyway because it's not even in the interval from -3/2 to +3/2. But I just want to make sure, because I'm going to try to do this with each rational function. So I want to make sure that we're being consistent here as far as looking at where the numerator equals 0 and where the denominator is equal to 0. But in this case, it's not in the domain of f, so it's not a critical number. Also not in the interval from -3/2 to +3/2. So for many reasons, x equals -2 is not going to do anything for us right now. So we only have one critical number to concern ourselves with right now, and that's x equals 1. So once you've found your critical number and you've looked for all the other ones you don't have anymore, you can go ahead now and look at your function value at your endpoints and the critical number that you obtained. In this case, you only had one of them. And again, I'm just going to keep popping these into my calculator. Just, make sure you're entering these appropriately with the appropriate grouping symbols. Make sure that you're using your parentheses. In the numerator, we have the quantity x squared plus 5, and in the denominator, we have the quantity x plus 2. It's our original function, not the derivative. Now, if you're wondering, like, why does she keep saying that? Why would we evaluate the derivative at the critical number? Well, you're going to be doing that in the next section, and then you're going to forget all about this, and then I'm going to have to remind you about it later. So we will get to a point where we're actually looking at the derivative and evaluating it at numbers, but that is not occurring right now. I go to my table. I'm going to look at -3/2, 1, and +3/2. And I'm going to get 14.5, 2, and approximately 2.0714-ish. Now, it's okay if you give me approximates here, as long as you can clearly tell me which one is the maximum and which one is the minimum. I'm not going to get all crazy about it and make you give me exact values. Someone told me, and I forget how to do it, but I think you can somehow make this a fraction here. Maybe you have to do it here? No. If you remember how, feel free to tell me, but there's some way that you can make it into a fraction. Oh, maybe if you, no, I had it entered as a fraction. No, I don't remember. But there's a way in your table to make it display as a fraction. Then you'd have an exact value, but I can't remember how to do it. It's been a while. I don't know. Anyway, again, you can hover over it though and look at the bottom if you need more decimal places for whatever reason. All right, so pick out the smallest value and pick out the largest. 2 is smaller than 2.0714. So we would say that the absolute minimum is 2, and that occurs at x equals 1, and the absolute max is 14.5. And since we already have this in our graphing calculators, I think we should look at this and actually kind of piece this together with what you're seeing on the graph. I always think that's a good idea. Now, the only window that I care about in this instance is from -3/2 to +3/2. So we're going to look at our function there. I also know that on the interval, my absolute max is 14.5, and my absolute min is 2. So I'm going to go to a window such that my x minimum is my left endpoint, and my x max is my right endpoint. And then for my y minimum, I already know that the minimum value is going to be approximately 2. Well, it actually is 2, but I know that I've got values here hovering around 2. If you want to look at this lower, you can. If you want to get a bigger picture, so maybe you want to start it at 0, that's fine. And maybe take your Ymax. If you want to take it up to 20, that's fine. 15, I don't know, 16. It's going to give you a small piece of this graph so that you can kind of see what it's doing on this interval. And when we graph it, that's what you're seeing. So kind of comparing this back here to your data, what we asked this window to be set at was an x-min of -1.5. Or, yes, x-min of -1.5. Sorry, I got that mixed up because of my function value being a max. But you're seeing here that your function has the absolute highest value here at this left endpoint. Whereas as we move to the right endpoint at +1.5, you're actually seeing that the function value here is going to level out at 1. And maybe we should have actually taken this a little bit farther to the right. Because notice that at 1, your function value is 2, whereas at 1.5, it's 2.0714. So I find that kind of interesting because it indicates that this function actually starts to go back up again and that the minimum occurs here. I'm kind of interested in that. So I'm going to take my x max maybe up to 3 just to see how much higher it goes. Now I'm curious. And it does start to go up very slowly, and it's hard to tell that. But you could, if you were looking to verify this, use that function in your calculator where you actually find the minimum value. And if you did that in here, you should be able to, it will tell you that the minimum is occurring at 1 and that the minimum value is 2. So kind of interesting to pull out the rest of this graph and see. And now that we've actually looked at the absolute max and the absolute min, if you want to look at the full picture again, go back to Zoom Standard, and you can see what's happening with your graph. And of course, we have this vertical asymptote occurring at -2. You're going to see another leaf to this graph down here if you expand it out further, which we're not doing. But yeah, but what we did was we just kind of narrowed in on this little interval from -1.5 to +1.5, and we found the absolute maximum. Actually, it was further up. It was up there, 14.5, and the absolute minimum on that interval. Had we gotten a different interval, we would have gotten different values. If I would have started this at 0, for instance, well, I would have had a different situation occurring. So that's just sort of the graphical representation of the data that we're seeing in our math. Okay. Questions there? Excellent.
So I did have a question.
Go ahead. Yes, please.
So right after you found the derivative, you set the numerator equal to 0 and then the denominator equal to 0 as well?
Yeah, so when we're looking at fractions, any sort of rational expression, if we want the rational expression to be equal to 0, we set the numerator equal to 0. If we want the rational expression to not exist, then we set the denominator equal to 0.
I see. Thank you.
I'm glad you asked because I do feel like this point kind of needs to be clarified a couple of times, just because it's different, I guess. So I'm glad you asked. Other questions on this one? Wonderful. Let's do another one. We are going to look at a radical function next. I promised you a whole bunch of different types of functions. That is what you are going to get in calculus today. F of x is 1 over the square root of x plus the square root of x. And we're going to look at this on the interval from 1/4 to 4. Now, kind of going back to that point that we were just talking about with rational expressions, one thing that I like to do anytime I notice that I'm going to have a variable in the denominator is I like to combine these to get one fraction, at least at some point. So if you want to wait until you find the derivative and then kind of pull these into one fraction together, that's fine. Because I really like to focus on looking at the numerator and denominator separately. Sometimes there are ways of solving these that cause you to lose something about your denominator that maybe you should have recognized. So let's find the derivative, and then we'll talk about rewriting this so that we can focus on looking at this function as one whole fraction. I also want to note right away that if x equals 0, your function is undefined. However, we're not looking at the interval 0. So I'm just going to make a note of it anyway. Note f of 0 is undefined. We cannot divide by 0. We might also want to note that the domain of this function can only include positive values of x, because if x is less than 0, then I can't take the square root of a value that's less than 0. And in this case, if x equals 0, technically I can take the square root, but I can't divide by 0. So I would say that this domain is only positive values. And like I said, you don't have to do this, but I think it's helpful if you start out by listing the domain. And when we do curve sketching in 4.6, we're going to always start out by finding the domain. So it's a pretty good habit to get into. Let's go ahead and rewrite the function so that we can take its derivative more easily. We'll have x to the negative 1/2 plus x to the positive 1/2. And once you've rewritten the function so that you have your rational exponents in order, go ahead and take the derivative. So we'll have negative 1/2 x to the negative 3/2 plus positive 1/2 x to the negative 1/2. Now, right away, you're probably going to say equals 0, and then you're going to stare at it for a minute and be like, okay, I don't know what to do with this function. How do I solve it? Well, you're going to start probably by turning this back into radicals. If I were you, I would start by at least making your exponents positive by moving your bases into the denominator. And I feel like we should be pretty comfortable with talking about x to the negative 1/2 as 1 over the square root of x. Do that. Now, you can solve this function from here if you would like. I told you I was going to try to be consistent with the way that I did this anytime I had rational expressions. So I'm going to stick to doing these all the same way, and I think it will be helpful for you also. To combine these into one fraction, you're going to need to get the same denominator so you can add these terms. I would also like for you to note, and I've mentioned this before, but it bears repeating, x to the 3/2 is x times the square root of x, because remember, it's just x times x to the 1/2. When you're multiplying and you have the same base, you add the exponents. 1 plus 1/2 gets you to 3/2. So I'm going to rewrite this a couple of times so that we can get this into a nice, workable expression. I don't want us to lose anything. This is honestly, I use this so often, all the time, sometimes even for higher values. Oh, this highlighter is terrible, but you might want to highlight it because you're going to use it all the time, I hope. It's my wish for you. These denominators would be exactly the same, except this one has an x in it. That one doesn't have just x in it. So if you want them to be the same, write equivalent fractions by multiplying in the numerator and denominator by x. And you learn to do this in your intermediate algebra class. And then you can combine these as two fractions. So go ahead and combine the numerators. I'm going to just write them in the opposite order. Instead of -1 plus x, I'm going to write it as x minus 1. And then the denominator is 2x root x. And you know what? Let's work on setting it equal to 0 in the next step. Maybe I got a little bit ahead of myself because I'm so used to doing that. So I'm going to put a box around my derivative real quick so I know which form I'm sticking with. See, I'm just like a robot, equals 0, but we're going to focus on both. F prime of x equals 0 when the numerator is equal to 0. Go ahead, Victoria, what's up?
Yeah, could you just explain how you got the 2x again from the 3/2 from the previous step before getting it to like combining into it being a 1 fraction?
Yeah, so, okay, so you can rewrite 3/2 as 1 plus 1/2, right?
Mm-hmm.
Okay, so if you do that, and you know that when you're multiplying with the same base, you add the exponents, you can split up x to the 3/2 so that it's x to the 1 plus 1/2.
Mm-hmm.
And then when you're multiplying with the same base, you add the exponent. So it's kind of like, sorry, I have arrows going in two different directions here. So these expressions are all equivalent. So I can take this, rewrite it like that, and then take it back up that direction.
Okay.
Maybe I should just
that makes sense because you're basically combining both of them together and multiplying them in a sense, correct?
Yeah, exactly.
Okay.
Yeah. So I'm just kind of, it's almost like I factored it in a way, if you want to think about figuring out an x and what that left me with.
Okay, cool. Thank you.
You're welcome. Other questions here? All right, so we got that. We're here. We know that f prime of x equals 0 when the numerator is equal to 0. And I know that happens when x equals 1. Well, go ahead and see if 1's in your interval. The interval that I gave you was from 1/4 to 4. Excellent. 1 is indeed in the interval. I'm going to box it up as a critical number. If you want, you can even label it as such so you don't lose it. And then we're going to talk about f prime of x does not exist, because remember, critical numbers are going to occur where f prime of x does not exist. What that means is your denominator is equal to 0. If you want to rewrite it back into its original form, if you find that helpful, do that. But this is only going to occur when x equals 0. So this only happens at x equals 0, and x equals 0 is not in the domain. It's not in the domain of f, and it's not in your closed interval. So we got two reasons why we're not going to call it a critical number, but the biggest reason why we're not going to call it a critical number is because it is not a critical number because x equals 0 is not in the domain of f. Okay. So x equals 0, not a critical number, but we had to look at it anyway, get into that habit, because that won't always be the case. Sometimes you're actually going to have critical numbers that occur in the denominator, and they will actually be defined in your original function. Questions there? All right, once you've done that, now you're going back to your robot self, and you're evaluating this function at the endpoints and at your, in this case, one critical number. You're going to put this in your graphing calculator if you'd like. If you feel like you're looking at this function and you're like, really, do I have to put this in my graphing calculator? It's pretty straightforward. That's fine. Don't put it in your calculator. If you feel like it's going to take you longer, that's fine. But if you are just like, I don't want to take any chances, I want to make sure that I actually get the right values here, I don't trust myself to do the arithmetic correctly, that's fine. Put it into your graphing calculator, get yourself some values. We've done a couple of these now. I'm going to tell you what my values are. 2.5, 2, 2.5. And I like this one because it's confusing to students. They're just like, wait a second, 2.5? I get that value twice? What does that mean? Well, that means that your absolute maximum value is 2.5, and it's okay that you got it more than once. Doesn't matter. It's still your absolute maximum value, regardless of how many times it appeared. And then 2 would be the absolute minimum value. Trying to remember the way WebAssign asks you for these. I'm pretty sure they just ask you for the value itself. Maybe I'll look in a couple minutes. I try to do these things while you guys are writing a bunch of stuff, so I have to try to remember to look. All right, questions on example C? Oh, I only have 2 more examples. Well, that's perfect because I don't have that much more time. Wait. Oh, good. 3 more examples. Thank goodness. The pages were stuck together, you guys. I would hate for you to lose out on the trig example that I was going to do last. Oh, no, it was a natural log. But the one I'm going to do next is for an inverse trig function. Yes. Oh, someone's got to get excited about this stuff. And since I cannot see you guys in person, if you're excited, I just don't know you are. F of x equals the inverse tangent of x. And we're going to look at that on the closed interval from -1 to 1. See if I can pull up this assignment and check it out. There it is. Yeah, so when you're working on these in WebAssign, it's going to ask you for the absolute minimum and maximum values. It looks like it doesn't actually ask you for the x values where they occur. I mean, obviously, you have to find the critical numbers in order to get them. But it's just asking you for absolute max and mins, which is kind of unfortunate, but such is life. Okay. We learned how to find these derivatives in the last section. So let's go ahead and find this derivative. 1 over 1 plus x squared. There's not a whole ton to do in this case. So we're going to look at 2 things. We have this in the form of a rational expression. F prime of x equals 0. Well, that means the numerator is equal to 0. That means 1 is equal to 0. Cannot be. 1 does not equal 0 ever. That happens sometimes where you end up with a situation where the numerator is not going to yield any critical numbers. So, okay, fine. We have no critical numbers from the numerator. So then you're going to take the denominator and say, okay, well, where does f prime of x not exist? That means 1 plus x squared equals 0, and that means x squared is equal to -1. That means x is equal to plus or minus the square root of -1. Well, we can't take the square root of a negative number. Okay, so that can't be. You can say it's non-real values or whatever you want to say. Either way, it's not going to happen. So we actually don't have any critical numbers, you guys. And that sometimes happens. That just means that inside your interval, you don't have any local extrema. That's okay. If you get a situation where that occurs, you're just going to evaluate your function at the endpoints and figure out which endpoint gives you an absolute max and which endpoint gives you an absolute minimum. And this one, I hope we can do without our calculators, but I don't know. Remember that an inverse trig function is asking you for an angle. So you're being asked what angle gives you a tangent of 1? Well, hopefully we know that's pi over 4. The angle that gives us a tangent value of -1, well, we talked about this on the first day where we were talking about domains of inverse trig functions. In our case, we're going to be looking at negative pi over 4. Now you can pop that into your calculator and it will give you a decimal approximation, and you can always go back and verify that that is indeed the case. So if you don't believe me, inverse tangent -1, and then if you're just like, is that negative pi over 4? You're just going to have to kind of double check it like that. Sorry, my light is starting to go, so that means I'm already dimmed out as far as I can go. But yes, you do end up getting that same value. The domain of inverse tangent, we talked about this a couple times, but we don't use it enough to really have it stick. Goes from negative pi over 2 to pi over 2. So your calculator knows that it's going to pop out the correct value. I do want to see something like this exact. I mean, if it was inverse tangent 2, then yeah, in that case, you can give me an approximate. But something like this is really one of those basic trig pieces of knowledge that I would expect you to give me exact values for. So if on a test you told me that this was equal to approximately -0.7854, I would probably take a point off and say, give me an exact value. I always want exact values if they exist. And in this case, they absolutely exist. And like I said, this is one of those pretty basic things from trig. So sometimes sometimes we need approximations if we need to compare exact values. But in this case, one of them's negative, one of them's positive. That should be pretty straightforward. This one's going to be your absolute min, and that one's going to be your absolute max. Right, you write that down. I'm going to switch my light over here. Hope it's not going to rain tonight. It's not usually this dark when class ends for me. Because it's going to be like 65 degrees tonight. You know what that means. I'm going for a run after class. Realistically, that will be like 11 p.m. Got to take advantage of these cool nights. And if it rains, clearly that's not going to happen for me tonight. I'll be sad. Okay. Questions on example D? No rain. Must just be cloudy. Right. All right, I got two more. One's an exponential and one's a log function. F of x is x squared e to the negative x, and we're going to look at this on the closed interval from 0 to 10. If you're thinking about the domain, your exponential function has a domain of all real numbers. Even if it's e to the negative x, does not matter. You can let x be any value, and you can take e to that value. And it is fine. So if you are thinking about your domain, we might as well go ahead and list that it is all real numbers. That means that if you end up getting a number that is excluded from the denominator of your derivative, then it will be in the domain of the original function, and we might have a case where we have a f prime of x dne in this case. Let's see. F prime of x, we're going to use the product rule. F prime g plus f. G prime, I had some people on the test who wrote g prime as e to the negative x, but it's negative e to the negative x because you have to use the chain rule. So be careful about that. I don't know if it was this exact function, but it was something very similar on your test. Minus x squared e to the negative x. And again, if you're kind of not sure how you would solve this, why don't you go ahead and write it as a fraction by taking this negative exponent and pulling your e into the denominator. There's not, one right way to do this. But we can write this as 2x over e to the x minus x squared over e to the x. When you rewrite it that way, it's kind of clear to see how you're going to combine this into one fraction. So you'll find that to be helpful. Oh, you know what? I'm not going to set it equal to 0 yet. I just wanted to rewrite my f prime. Trying to be consistent about this. All right, questions about f prime? So first we're going to look at where f prime of x equals 0. That's going to happen where the numerator equals 0. Factor it to solve it. I would strongly suggest not adding x squared and dividing both sides by x. You don't want to lose any possible solutions. Let's see what happens, and then I might show you the wrong way to do this. Take out the x, and that leaves you with 2 minus x equals 0. Yeah, I will show you the wrong way to do this. Okay, so notice how I solved this by factoring. And when I did that, I got x equals 0 and x equals 2. 2 minus x equals 0 gives us x equals 2. That's two solutions. Now, technically, 0 is not a critical number because it's one of your endpoints. If it's your endpoint, then we don't consider it a critical number. So maybe I boxed it prematurely. It's kind of a tricky one. But we're not going to include it as a critical number, but we are going to be evaluating it regardless because it's an endpoint. Now, let's say you solved this the other way. This is what I sometimes see students do, and I want you to be careful with this. They add x squared on both sides, and then they divide both sides by x. You don't want to do that because notice how in this case, even though it worked out fine in our case, it only worked out fine because 0 was an endpoint. So you didn't need the 0 anyway. But let's say I set this to start at -1. Well, you would have lost your 0. You would have lost a critical number. When you divide by a variable, you're going to lose a solution. So don't do this. Put a cloud around it. Don't divide by a variable. Or I should maybe say don't divide out a variable. Like don't cancel it out. Because we lost solution x equals 0, because we lost x equals 0. So be careful with that. That's why I always solve these by factoring. I don't want to lose any solutions. Okay. Questions about f prime of x equals 0? F prime of x does not exist when the numerator equals 0, or I'm sorry, the denominator equals 0. And that would be e to the x. Now, if you're not sure, and you're going to get used to doing this, by the way, you can always get the variable out of the exponent by applying a natural log on both sides. However, the natural log of 0 does not exist. So if you say x equals the natural log of 0, well, now you've entered into a mess because natural log of 0 does not exist. You can put it into your calculator and verify, but if you're going to do that, oh, it gives you a domain error. So it'll say error, domain. That's because the domain of a natural log function is only positive numbers. Domain of ln x is from 0 to infinity. So in this case, we don't actually have any values that make f prime of x not exist, because you can't get a situation where e to the x equals 0. And e to the x is never going to equal 0, because think about what the graph of e to the x looks like. If you haven't seen it in a while, that's fine. I'm going to show you right now. It looks like that. And it's got a horizontal asymptote sitting here on the x-axis. E to the x can never equal 0. Ever. The range of e to the x is the domain of the natural log of x. The range of e to the x is all positive numbers. So e to the x can never actually attain the value 0. So you don't have any issues here with your denominator. So we have one critical number, and that's at 2. The critical number we got at 0 was actually an endpoint, so we are going to test it as an endpoint. So we're looking at f of 0, f of 2, and f of 10. And you can pop these into your calculator, but you should come up with 0. And again, I like exact values, but you might have a hard time comparing them if you don't get their decimal approximations. I'll be clear about that on a test when approximations are okay. So 0 is your absolute min, and approximately 0.5413 is going to be your absolute max. All right, I got 3 minutes, and we should be pretty good with these by now. So let's do a natural log, and then we will be done for today. F of x equals x, natural log x. I want to remind you that the domain of a natural log function is only positive numbers. So your domain here is restricted to the domain of the natural log. Okay, let's go ahead and take the derivative. F prime g plus f g prime is the natural log of x plus 1. And we're going to look at 2 things. We're going to look at where f prime of x equals 0 first. F prime of x equals 0 whenever our derivative, natural log x plus 1, is equal to 0. So that means the natural log of x is equal to -1. Now, don't get confused between the domain and the y value. The range of the natural log function is all real numbers. So we can actually obtain a value for x here. If you're not sure how to solve for the natural log, just raise both sides with e as the base. and this gives you x equals e to the negative first. Personally, I like to write that as 1 over e, but either one of those is fine. If you're not sure whether it's in the domain, e is a positive number. If you take a positive number and divide it by a positive number, it's still going to be a positive number. So it is in your domain. Oh, I didn't give you an interval. Yikes. So we're going to look at this on the interval from 1 over e squared to e. Okay. So if you're trying to figure out, well, 1 over e squared to e, I'll give you some approximate values. 1 divided by e squared is approximately 0.1353. And then e, some of us know and others have not seen it in a while, is approximately 2.718. So there's your interval. And 1 over e is approximately 0.3679. So in a case like this, it's helpful to use approximates just because you need to be able to make sure that your value actually fits into your interval, which in this case it does. So we're going to put a box around it, and that's our critical number. And, you know, this kind of is obvious, but you don't have a denominator. You don't have any values where your derivative does not exist. In this case, we'd have to exclude any value that wasn't in the domain, but it's not going to be a critical number for us. So we would say nowhere. And then you're just going to test this function at the endpoints. If you want to think about 1 over e squared as e to the negative second, if that makes it easier for you to enter into your calculator, that's fine. And then that's your critical number. And then there's e. Now, keep in mind, WebAssign might ask you for exact values. If they accept approximates, great. The approximates, when you put them in your calculator, look like this. If they don't accept the approximates, then you're going to have to enter exact values. So remember, you're just going to have to evaluate your function at these values. So f of e to the negative second is 1 over e squared times the natural log of 1 over e squared, just going back to your original function. And then you'll just have to come up with the exact function value. And actually, that's going to be easier to do if you leave that with a negative exponent. This is negative 2 over e squared. Remember, the natural log of e to the x is just x. So the natural log of e to the negative second is just going to be negative 2. So I don't know if they're going to want actual values. They're pretty loose about what they accept. But if they do want actual values, then you will know what to do. Negative 1 over e, and then f of e is going to be e times the natural log of e, which is just e. Okay. Oh, now I owe you 2 minutes, but that was it. I'm done. I'm going to record for you guys an asynchronous lecture. However, it's not going to rain tonight. I'm going for my run, and I'm not recording a lecture afterwards. But you know what? You're not going to watch 2 lectures in the space of 24 hours. So I'm going to record my lecture tomorrow afternoon, and it will be posted by your normal class time. Not that you have to watch it in that time, but I feel like 24 hours between lectures is perfectly acceptable. So sorry if you like to watch these on Friday mornings. You will be able to watch it Friday night because you have nothing else going on, right? No plans Friday night. You could totally watch your asynchronous lecture then, or Saturday or Sunday. Yes, you would only have 1 lecture to watch this weekend, just like every weekend. So nothing too crazy. I'm going to record something for 4-3 we'll see how long it takes. We might start getting into 4.4 a little bit. I'll kind of see how it goes. But I'm going to record it tomorrow afternoon. I'm going to post it so it'll be up by tomorrow night so that you can plan your Friday night accordingly, and or your Sunday morning, or whatever it is, whatever you want to watch it. But I'll put up a homework assignment now for 4.2, and I'll email you when your asynchronous stuff is up. Okay. Email me if you have questions though, and have a wonderful weekend, you guys.
We have a quiz on Monday, right?
Yes, you have a quiz on Monday. I'm glad you reminded me.